Welcome to the seminar. It's my pleasure to introduce today's speaker, Professor Alexander Zheglov from Lomonosov State University, and he's going to speak on the theory of normal forms of differential operators and some of its applications. Please.
Thank you very much for the introduction. First of all, I would like to thank the organizers of the seminar for inviting me to make a talk here. And I'd like to present some results, recent results about the theory of normal forms of differential operators, which I got by myself and as well as together with my collaborators, and some of its applications which might be of interest to you. I mentioned these applications in my abstract. So I hope everybody will enjoy. I will try to do the best. And please free to ask me any questions. My talk will be based on a series of works. They are listed on the slide. I hope the slides are visible, right? Okay. So these results are based on the series of papers you see on the slide, starting from 2023. A paper by myself, 3 papers written with my PhD student, Zheglov. My recent preprint about the Dixmier conjecture, and one relevant paper written together with Igor Bourbon about Kohn-Macaulay models and quasi-invariants in Algebra model systems. To start, let me introduce some notation. I will use it through my talk. K will be a field of characteristic 0, and for some applications, one can just assume for simplicity that K is a field of complex numbers. By R hat, I will denote the ring of formal power series in n variables. For most part of my talk, n will be equal to 1. However, some parts of this theory were developed for any dimension. By Dn, I will denote the ring of differential operators with coefficients in the ring R hat. It's a very simple ring with usual commutator relations. Dn, di is a derivative with respect to the variable xi. And Dn hat sim will denote some universe ring, which I will define below. This is a ring. It was first invented in my paper with Igor Bourbon, I mentioned on the previous slide. And this ring appears to be a very convenient tool for studying quantum integrable systems in broad sense. In particular, we studied certain quantum Algebra model systems and their deformations inside this ring. Now let me introduce the definition of this ring and some of its properties. Since the most part of my talk will concern only dimension 1, I will sometimes use the same notation for the ring of power series in one variable and in n variables. So for one variable, let me just consider the following vector space. This is an infinite dimensional vector space consisting of all formal power series. The coefficients of this power series are just element of this ring R hat, which is just ring of formal power series in one variable for this item. Here, V of A is a discrete variation, or just the degree with respect to x, the degree of 0. at 0 point of the series A. And let me define in this situation the order function. I define the order function on this infinite dimensional vector space to be the supremum of all integers k, non-negative integers k, the supremum of the following values k minus v of a k. So the order is the supremum of all these numbers running over all terms in this sum. Certainly, if you take an arbitrary series in this infinite dimensional vector space, this order function can be infinite. But we define the ring D1 hat sim as a vector space consisting of those series in this infinite dimensional vector space which have finite order. It appears that this infinite dimensional vector space is a ring, associative ring, and we can define an analog of the highest symbol as in the classical theory of differential operators. The highest symbol is defined as a sum of homogeneous components with the same order, which is equal to the old order of Q. If Q is an element of this ring, then it has finite order, and therefore we can define this highest symbol. So the multi-dimensional analog of this ring can be constructed just in the same way. We consider now the infinite dimensional vector space of series where D underline and AK are now the products of the i's with multi-index I, K, and AK are elements of the ring R hat, where R hat now is a ring of formal power series in n variables. In the same way, I can denote by V the discrete valuation of this ring of formal power series, which is defined by the unique maximal ideal M generated by x1, xn, and denote by this symbol the sum of indices in the multi-index K. I can define in the same way as above the order function of this infinite dimensional vector space Mn as a supremum of all numbers of this type. So again, this number can be either finite or infinite, and I define the ring Dn hat sim as a vector space, those elements of this infinite dimensional vector space which have finite order. So this definition is very simple and purely algebraic. Let me mention certain properties of this ring. First of all, this is a ring, this is an associative ring with natural operations of multiplication and addition coming from the ring of differential operators Dn. One can easily observe that this ring contains, the ring Dn hat sim contains the ring of differential operators as a dense subring. So there is an obvious topology on this ring determined by this order function. And then Dn is a dense subring in the ring Dn hat sim. I call it as a Dn hat sim because it's a kind of symmetric completion of the ring of differential operators Dn. Symmetric in the sense that it doesn't depend on the order of variables x1, xn. Then one can observe that R hat has a natural structure of a left Dn hat sim model, which extends its natural structure of a left Dn model. And it's convenient to think about the ring Dn hat sim and the ring R hat as a ring of operators acting on a ring of functions. This action is defined by this natural left Dn model structure. Next property is that this ring appears to be very big. It's really very big. It's not necessarily in any sense, and it contains many useful objects. For example, certain operators from this ring can realize continuous endomorphisms of the K-algebra R-hat, Dirac delta functions, differential operators, operators of integration, difference operators, universal enveloping algebras, etc. The idea to study quantum integrable systems of various types, and under quantum integrable systems, I understand certain commutative subrings of differential or difference or integral differential operators or subalgebras, universal enveloping algebras. The idea is to consider these subrings as a subrings of this big ring D hat sim and then apply certain theory of normal forms, which I'm going to talk about today. So now let me introduce some examples of typical operators belonging to the big ring D hat sim. The typical example is a shift operator P alpha. It can be constructed in a very simple way. It's just a sum of such sort. And everybody can note that this sum is just a Taylor expansion of this operator, where star here means that we consider this exponential function as a function of commuting variables. So we take the exponential, usual exponential series, Taylor series of this sum, then consider the normal ordering, where the products of the i's stand on the right, each monomial, and the products of ui's stand on the left, and then you get this series. And in the exercise to check that this operator P alpha acts on any element of any series from the ring R hat just by shifting arguments. So in this definition, of course, to make it correct, we need to assume that ui's are elements belonging to the maximal ideal. So here ui's belong to the maximal ideal generated by exponents. So this typical example of a shift operator can be specified, further specified for, say, situation when the n is equal to 1. And I will need the following examples of operators to explain the theory of normal forms in the ring D1 hat sim. So for one variable. For one variable, let's psi be the k's primitive root, k is some natural number. Then we can construct the following operators by the same receipt as above. So delta is just an operator given by this series. One can easily observe that this is a homogeneous operator for the zero, because the powers of x and powers of d are the same at each monomial, so the difference of n and l is 0. And as this example above shows, when we apply this operator to a function f of x, we get just the value of this function at 0. So delta is a realization of a Dirac delta function. Then if you consider an operator given by this series, one can observe that again this operator is homogeneous of order -1. So it's well defined, it belongs to the ring D1 hat sim. And another easy exercise is to observe that this operator acts on each power of x as an integration, so it's a realization of an integral operator, integration operator. At last, I'd like to define a sequence of shift operators of the following type. We can take the operators of the following type. That here again the exponential. This notation means the same as above. So same receipt. We take the exponential of this monomial, and then consider normal ordering and get an operator. Again, according to this receipt, one can check that these operators realize multiplication shift operators. So when we apply this operator to any function, the argument of a function will be multiplied by psi power I. So k here is a fixed natural number, psi is a fixed case primitive of unity. So obviously the case power of any such operator is 1. All these operators I will need to formulate several major theorems from the theory of normal forms. So now let me explain a couple of major theorems from so-called generalized Schur theorem. These theorems were invented in my first paper listed on the first slide about Schur theory. Let me introduce one notation. I will denote by F the right d NHC module. I will call it as a spectral module. It is just a factor of d NHC by the right ideal. And one can notice that as a vector space, this module is isomorphic to the space of polynomials in derivatives 1 to 1, d1, dn. The first theorem, which I call a generalized Schur theorem because it sounds exactly like a very well-known Schur theorem from the beginning of 20th century. It says that if you have n commuting operators in this ring D1 hat C with the same order K, and if the spectral module F of the ring generated by highest symbols of these operators is finally generated and free, then there exists an invertible operator S for the 0, such that the simultaneous conjugation by these operators transforms the operators pi to the powers of the derivations di. Let me emphasize that this condition to be finally generated and free is usually satisfied for all known examples of cohomology systems, which I studied with my collaborators. So this is not very strong condition. Usually it is satisfied for many examples. To formulate the second theorem of this generalized Schur theory, let me introduce another new notation. Again, let K be a fixed natural number. Let me fix a primitive case root of unity. And again, I can define a generalization of these shift operators on the previous slide. So on this slide, I define the shift operators depending on one variable, and we can generalize their multidimensional analogs as well by the same formula. Now K here is the same fixed number I, K, natural number K. I is just a power of psi K. And Q is index of a variable. We define the same shift operators, and also we define analogs of integration operators with respect to the variable Q. Then the second theorem, the centralizer theorem, says that the centralizer of operators dq power k consists of operators of the following shape. Precisely, if you have an operator q which commutes with all powers q dq power k, then it must be a non-commutative polynomial of the following type. So here I fix the order, some rule, writing down this non-commutative operator. It's a non-commutative polynomial in three types of operators. Operators a, k, j, I, operators of integration, and operators of differentiation. C, I, j1, jn are polynomials in dq and integration operators. They are polynomials with constant coefficients, and this non-commutative polynomial q has restricted orders with respect to each operator dq and integration operators integral q. So this is a non-commutative polynomial of restricted order with respect to any variable. And this theorem appears to be very convenient to introducing the notion of a normal form and developing some technique which appears to be very useful for many applications. So let me explain what happens for n is equal to 1 dimension. If n is equal to 1, then the conditions of the generalized Schur theorem are automatically satisfied for any regular operator. What means regular operator? The regular, an element P is called regular if the following map is injective. Sigma of phi is the symbol of the operator P, and the map sends an element F from the spectral module F to F dot sigma. So in this case, when P is a regular operator, there exists a Schur operator such that P is equal to S d power Q S minus 1 for some S. In this case, the centralizer theorem can be further specified. Namely, it can be shown that there is an isomorphism of rings, centralizer of d power k in this ring, d1 hat c, is isomorphic to a matrix ring, k by k matrices, with entries from the ring of polynomials in one variable. C of dk denotes here the centralizer of the operator d power k in the ring d1 hat c. And this isomorphism appears to be, first of all, it can be very explicitly given. I have no time to write down all explicit formula, but however it can be done. And this isomorphism appears to be very convenient for calculations. Now, so if there are any questions, please let me know. Now I'm ready to explain what is the notion of normal form. What is a normal form? A pair of differential operators. So now let P and Q be a pair of regular operators on the ring of differential operators. Now I consider again situation of dimension 1. PQ are ordinary differential operators. And let S be the Schur operator for operator P from the generalized Schur theorem. Then we'll call the operator Q tilde of this form with a normal form of Q with respect to P. The normal form is not uniquely defined, but after conjugation with invertible Schur operators from the centralizer, order 0. By the centralizer theorem above, such S is a polynomial of restricted degree with respect to all variables. And any such operator is given via the isomorphism on this slide. Any such operator is given via this isomorphism by a lower triangular matrix with constant coefficients. Any normal form can be normalized in some way. For example, we can put some coefficients, some entries of this matrix presenting this normal form Q to be equal to 0. In any case, by the centralized theorem, this normal form consists of non-commutative polynomials. And as we will see, the normal forms of operators from some commutative ring B appears to be a very effective tool for a description of moduli space of spectral sheaves. What is a spectral sheaf? I will explain it below, but now let me give one example. This is an example of a normal form for a pair of operators. I consider the pair of commuting operators L and P. This is a very well-known Wallenberg's example. Due to Wallenberg, it's the end of 19th century. The first operator is a Schrödinger operator, D or 2 plus U. P is an operator of the third order, where U is some function, a potential, which I will decompose the Taylor-Barrow series. It is very well known that L and P commute if and only if the KdV equation is satisfied this potential U. And if they commute, the spectral curve of these operators, but it's very well known that any pair of commuting differential operator are algebraically dependent. The algebraic dependence can be explicitly written. I will explain it in more details below. And in this, for this particular example, this algebraic dependence is given by the following equation. This equation determines the so-called spectral curve. In this case, it's just Weierstrass cubic curve. So it's either elliptic curve or some degenerations of elliptic curve. And the coefficients can be written quite explicitly. Then in this situation, we can calculate the normalized normal form. Normalized in this example means that the second coefficient of this operator is 0. So the normalized normal form of P with respect to L can be given by just this explicit formula. It can be rewritten in matrix form or in some other forms. However, let's see how it looks like. Now, let me give a general definition of a spectral curve and a spectral sheaf. Explain how we can parameterize spectral sheaves and spectral curves with the help of normal forms. A spectral curve is any irreducible projective algebraic curve for the field of characteristic 0 that has a regular key point. And a spectral sheaf is a torsion-free sheaf on a spectral curve with vanishing cohomology. So these notions are familiar, very well known from the theory of commuting ordinary differential operators. This theory has a long history. It started from the sample papers by Birch and Chondi. Then this classification was reopened by Krishever, and he gave a classification of commutative subrings of ordinary differential operators in terms of so-called spectral data. And then this theory was elaborated by many mathematicians. Mountford, Sato and his school, really many papers. And so this terminology came from this theory, spectral curve of commuting differential operators, and spectral sheaf is a sheaf field we are in this classification construction. However, we can consider the following problem, generic problem, how to parameterize such sheaves. So if you don't know anything about the commuting differential operators, you can just consider some irreducible projective algebraic curve and all torsion-free sheaves with vanishing cohomology group. Question is how to parameterize such sheaves. It's a part of modeling problem. The explanation of terminology is given below. So, namely, if P is a regular K-point, then the data CPF essentially determine an elliptic commutative subalgebra of the ring of following differential operators. What is an elliptic commutative subalgebra? I will explain on the next slide. The points of the curve parameterize common eigenvalues of commuting operators, and fibers of the spectral sheaf parameterize the spaces of common eigenfunctions on these operators. Now I will explain how we can parameterize such sheaves with the help of normal forms. So first, let me recall a part of classification theorem, commuting differential operators. We say that an ordinary differential operator P of positive order is called formally elliptic if its highest coefficient belong to the field K, invertible, and a ring containing an elliptic element is called elliptic. It is very well known that given any operator P with invertible highest coefficient, there is a change of variables, so-called normalization, such that after this change of variables, or in other words, after an application of an automorphism, we get a normalized differential operator. Differential operator which is monic and which has a zero coefficient at the power n-1 is called normalized. And now if P is a commutative subalgebra of differential operators containing an elliptic element, then all elements of P are elliptic. Very well known lemma. And now let me recall the classification theorem due to Khrushchev, Mumford, and others. So this classification theorem says that there is a one-to-one correspondence, where this one-to-one correspondence is established via very explicit construction between the following data. Equivalent classes of commutative elliptic subrings of ordinary differential operators of rank R, and algebraic geometric data, spectral data on the right-hand side up to isomorphism. In the case of rank 1 rings, this one-to-one correspondence can be specified, and this classification can be reformulated in purely geometric terms. So here, the rank of the ring is a great common divisor of all orders. The equivalent class of commutative elliptic subrings consists of the following rings. So we say that two rings are equivalent if they are related by conjugation by an invertible function. This Weyl equivalence relation means that we consider this equivalence class additionally up to a scale transform, the following type. And the spectral data consists of the following objects. So let me formulate this. So C here is an integral projective curve. P is a closed regular K point. F is a covariant torsion-free sheaf of rank R on C with vanishing cohomology groups. And the rest of this data is some local data, local formal data. Z is a local coordinated P, and phi is a formal trivialization of the sheaf F at P. Since P is a regular point, the completion of F at P is isomorphic to this model K of Z plus R, where R is the rank of data. Here we have the following isomorphisms. If we delete this specific point P, then C minus P will be isomorphic to the spectrum of the commutative thing P. This is a part of correspondence, part of this construction. To define the one-point complication of this curve spectrum B, we need to consider natural degree filtration on B, consider the Oris ring B tilde, and take the projectivization, the approach construction by Grotin. Sorry, this is a misprint here. That should be approach B. For example, if commutative ring B is generated by just two operators, P and Q, then the fine spectral curve is just a plane curve defined by the Birch-Chorny polynomial. What is Birch-Chorny polynomial? A Birch-Chorny polynomial is a reducible polynomial F, which has the following shape. It was invented by Birch-Chorny at the beginning of 20th century. For any pair of differential, for any given pair of different commuting differential operators can be explicitly written down as a differential resultant of a pair of operators. And the equation given by this polynomial, y is equal to 0, determines an affine spectral. So from this classification theory of commuting operators, it's known that an irreducible polynomial F given an algebraic relation between commuting operators prime and Q prime is a polynomial Birch-Chorny type. So this is a generic classification theorem. One-to-one correspondences here are quite explicit. I have no time to explain them, but now I'll try to explain how these spectral sheaves can be parameterized by the normal forms. And then I'll formulate a new version of this classification theorem in terms of normal forms, which is rather simple and simpler than this theorem because it formulates a classification in purely algebraic terms so that nobody, so that it must be clear even for undergraduate students which don't know anything about spectral curve or algebraic geometry. Now let me recall a couple of other interesting theorems from this theory of commuting operators. For a pair of commuting operators, there is a theorem of Wilson, which says that if R is a rank of a ring commuting differential operators generated by P and Q, the Birch-Chorny polynomial F, which is equal to this differential resultant, then F is a R power of a unique reducible polynomial satisfied by P prime and Q prime. It can be proved, it's just elementary algebra, that this Birch-Chorny polynomial F, which is equal to the differential resultant pair of operators, it's just the determinant, the characteristic polynomial of the normal form Q tilde prime is the normal form of Q prime with respect to P prime. If you take its matrix realization and calculate the characteristic polynomial, then we get just the same polynomial. So this fact connects theory of normal forms with classical theorem by Wilson of the theory of commuting differential operators. Now I'm ready to formulate the theorem, the first result, first application of normal forms. To formulate the theorem, I need to introduce another definition. It's a definition of normalized normal form. First of all, as I said above, for any given operator from the centralizer, we can choose some normalization. So normalization means an appropriate representative in the matrix conjugacy class. For example, we can put some entities of matrix representing this operator to be equal to 0. If we fix such a normalization, we will call such a representative as a normalized operator. Then the definition of a normal form can be generalized to the case of commutative subrings. Namely, let's call a commutative ring D prime. Now this is a subring of centralizer, and the ring D1 has sim generated by operators P1 prime, Tn prime. As a normalized normal form with respect to some ordered set of generators, and we will call the coefficients of the operators Pi prime as coordinates of P prime. So we have a commutative ring, it's finitely generated. P2 prime is normalized somehow. Each polynomial, each operator here is a non-commutative polynomial, so it has finite number of coefficients. And let's call these coefficients as a coordinates of P prime. So since all these operators are algebraically dependent by Birch-Chon lemma, the algebraic dependence is by this characteristic polynomial. We have certain algebraic relations on the coefficients of the coordinates of this operator. Now let me denote by x P prime the corresponding affine algebraic set determined by these relations on coefficients of operators Pi prime. But it can be shown that it's defined by an isomorphism class of the ring P prime. So a theorem which permits to parameterize spectral sheaves, that is torsion-free sheaves with vanishing cohomology groups. This parameterization, this classification can be formulated in short as follows. There is a one-to-one correspondence. Again, this correspondence can be given by an explicit construction. The one-to-one correspondence is between normalized normal form B prime in the sense above, such that the spectrum of B prime is isomorphic to a fixed affine spectral curve, and triples up to the natural isomorphism. In particular, this isomorphism indicates that the modulus space of spectral sheaves, that is torsion-free sheaves with vanishing cohomology, is an affine open subset of the modulus space of semi-stable torsion-free sheaves with fixed Hilbert polynomial. So one can show, it's easy to see that sheaves with vanishing cohomology groups are semi-stable, and the Hilbert polynomial of this sheaves is fixed. In this theorem, it's absolutely not important whether the curve, the spectral curve, is singular or not. So it gives this one-to-one correspondence for arbitrary singular curve. In the case of a smooth curve, we get a very well-known description say, in the case of rank 1, we get a variable known result that a complement to the theta divisor is a fine set. But for singular curves, we get some explicit way of arbitraging, determining the fine set, arbitraging such sheaves. Let me give here one example. Let P and Q be a pair of coprime numbers. Then any normalized matrix, normalized in the sense that we can put sum of integers of this matrix to be equal to 0, is a normal form of some differential operator Q of order Q with respect to some differential operator P of order P. All such matrices form an affine space AN, just parameterized by integers of this matrix, non-zero integers of this matrices. So any point Q tilde of this affine space parameterizes a spectral sheaf on a projective curve. Which curve? This curve is a one-point complexation of the affine spectral curve given by the characteristic polynomial. If we fix the equation of curve, then we get some affine subset parameterizing spectral sheaves on this curve. But now I can give one new result. This is an alternative version of the classification theorem of commuting differential. Let me consider the following very simple situation. I'll classify only commutative subrings generated by two operators of rank R. In this case, the classification theorem has the most simple form. The theorem, now that's a joint result with my student, Weyl, says that there is a one-to-one correspondence between equivalence classes of rings of commutative operators of rank R in the same sense as above. So two rings are equivalent if they are conjugated by an invertible function. Where the order of P is Rp and the order of Q is Rq, where P and Q satisfies the torsion equation FPQ equal to 0, and triples P tilde d power Q and S tilde. P tilde is a matrix, normalized matrix, satisfying the same torsion equation. So some relation. And S tilde is some auxiliary operator, which can be written as a formal power series with vector valid coefficients. So a K is any vector from this ring. And this S is normalized. Normalization here means that we set some prescribed coefficients of all these vectors to be equal to 0. So S can be thought of as an infinite number of free parameters. And that is all. So again, this one-to-one correspondence is very explicit and can be given by explicit algorithm. Moreover, all operators, all steps of this construction can be programmed, and they are already programmed by my students, John Hugo, so that one can calculate either a given either a triple or any given commuting pair of operators, or vice versa for any given matrix and any given S with any value of these free parameters. You can calculate a pair of commuting operators up to any prescribed order. This classification is somewhat simpler because here we need only to write down some matrix and set up infinite number of free parameters. If you omit this condition, so if we consider just arbitrary matrices and arbitrary set of free parameters. Then we establish a one-to-one correspondence between all possible rings of commuting differential operators generated by a pair of operators P and Q. Next application of the theory of normal form is a description of one-to-one correspondence, again, explicit one-to-one correspondence between the solutions to the string equation and pair of commuting differential operators. This is another topic. The solutions to the string equations were studied since 90s. The string theory by many physicists and mathematicians. And my construction extends and reopens the well-known construction by Albert Schwarz from the 90s. Again, let's consider the ring of differential operators. Recall that P is called normalized if it has the following form. That means that it is monic and the next coefficient is 0. And let's consider this so-called string equation. It's an equation which is written here. Commutator of Q and P is equal to 1. Any solution to the string equation can be normalized, and it's called normalized if a P, operator P, is normalized. And analogously, I will call a pair of commuting operators P prime and Q prime normalized if P prime is normalized in this sense. The next application of theory of normal forms is a theorem which establishes a one-to-one correspondence between solutions to the string equation and the pairs of commuting operators under some condition. So namely, there is a one-to-one correspondence, again, which can be very explicitly described, between pairs P and Q and P prime and Q prime, where P and Q is a normalized solution to the string equation, satisfying the so-called termination condition for the head-chopping process. I'll explain what does this mean below. And P prime and Q prime is a pair of commuting normalized operator of the same orders, satisfying analogous termination condition for the head-chopping process. This construction, this one-to-one correspondence, appears to be the key point and the proof of the Dixmier conjecture. This is the last application I'm going to talk about. A similar correspondence for pairs of operators of coprime orders was early established by Albert Schwarz. And he called a solution to the string equation as a quantum curve. Quantum curves were also studied by many mathematicians in 2010, 15, etc. So now let me explain what means the termination condition for the head chopping process. So given operators P and Q of order P and Q, let's consider the following recurrent sequence of polynomials, which is given by this formula. I take the operator Fi of xy, take its P's power, and divide the x power mi multiplied by some appropriate coefficient. This sequence of polynomials is constructed by this formula. The initial polynomial is just y, and then 0 is just q. The numbers epsilon, r, and mi are defined in such a way that the order of this new reconstructed operator is strictly less than the order of the operator of I power p. And I will say that the operators P and Q satisfy a termination condition for the head chopping process if the sequence of operators Qi, these are Fi of P and Q, satisfies the following conditions. The sequence of great common divisors of the orders of all these operators ends by 1. And the distance of PQ, which is defined by this formula, is less than p plus q. So here the distance is just the sum of the following brackets: ni dot order of fi pq minus order fi plus 1 pq. I call this process a head chopping process because I apply this process the normal form of the pair of operators p and q. If we go to the normal form, we get the power of d and some non-commutative polynomial q. I imagine that the q is an operator which has a head, the highest symbol is a head, the rest of it is a body, and this process is just the usual algebraic process of head chopping process, where we cut off heads of each next non-commutative polynomial, and so we get some sequence of operators. So now I gave a formal definition of this head chopping process, and now I can explain the construction of this one-to-one correspondence. It uses a theory of normal forms. Namely, if we start with a solution to the string equation, we can find a Schur operator such that after conjugation by the Schur operator, we get a normal form. Then we can cut the tail of this normal form. What is the tail? I will explain on the next slide. Get another normal form, and then I can again find another Schur operator which transforms this normal form to a pair of commuting differential operators. And vice versa, given a commuting pair of operators, I can find a Schur operator, construct a normal form, glue some tail, get another normal form, find another Schur operator, and get an operator PQ. All these steps are explicit, can be calculated, and I will show some examples below. So in more details, this middle one-to-one correspondence between normal forms, called gluing the tail and cutting the tail, can be explained as follows. If you have a pair of commuting operators, a solution to the string equation, and if you consider a normal form of q with respect to p, then according to the centralized theorem, q theta is a non-commutative polynomial, where the blue terms qi belongs to the centralizer, and the last term, which is red, has the following explicit form. It is uniquely determined, and I will call it the tail. So now this correspondence looks very easy. If I have a normal form of a solution to the string equation, then cutting the tail means that I just divide this tail, and gluing the tail means that I add the tail again to the commutative normal. Let me mention some results about this one-to-one correspondence. This determination condition for the head chopping process holds for solution to the string equation from the first-layer algebra of subrectangular type. I will explain this below. Or for operators determining an automorphism of the first-layer algebra. Not all solutions to the string equation satisfy this condition. Quite recently, one student wrote me an email claiming that it found a series of examples. I checked these examples. These are really the examples, which violate this condition. So these examples cannot be obtained from pairs of commuting operators. At last, if commuting operators satisfy the termination condition for the head chopping process, then necessarily the rank of the ring of commuting differential operators is 1. So an interesting question, which is still open, how to classify all solutions to the string equation. I think that it's interesting from the point of integrable systems. Let me show some examples. And I know that my time is over, but I hope that I have a couple of more minutes to explain the last application. Sorry for that. So put gamma to be equal to xd, and let me consider certain solutions to the string equation given by an automorphism of the first Weyl algebra. The simplest automorphism is given by a pair of operators P and Q of the following type. So they are of coprime orders, order of P is equal to 1, order of Q is equal to 2. In this case, the normal form of Q with respect to P is equal to Q itself. The tail is minus gamma integral. And so, cutting the tail, we get the corresponding commuting operators. These are operators with constant coefficient. Another example, if we consider the solution to the string equation given by the automorphism of the first Weyl algebra given by these two operators, in this case, P is equal to 2, the order of P is equal to 2, the order of Q is equal to 1. We can consider again the normal form of Q with respect to P and the tail. The tail is now given by the following explicit formula. The normal form of this pair is given by this formula. Cutting the tail, we get again a pair of commuting operators, which are operators with constant coefficients. The claim is that for any automorphism of the first Weyl algebra, this construction gives the pair of commuting operators with constant coefficients. So as a third example, this is a more non-trivial automorphism of the first Weyl algebra. In this case, again, the tail is given by the same formula. The normal form of this pair is given by this formula, and cutting the tail, we get a pair of operators with constant orders. In the third example, the head chopping process, the determination condition of head chopping process satisfied, and the head chopping process consists of two steps. In the example 1 and 2, the head chopping process consists of one step. So that's because the orders of these operators are coprime. Well, the last application, very briefly, of the theory of normal forms is a proof of the Dixmier conjecture for the first Weyl algebra. Let me recall that a first Weyl algebra is just a ring of differential operators with polynomial coefficients. Analogously, we can define the nth Weyl algebra. And famous Dixmier conjectures says that any endomorphism of a K algebra in N is an automorphism. In fact, Dixmier proposed his conjecture only for the first Weyl algebra. Other conjectures, also they are very clearly formulated as a folklore. I don't know exactly if Dixmier really supposed all conjectures. I haven't found the source of it. And analogous Jacobian conjectures were familiar, are defined the series conjectures for n greater or equal to 2. They said that any polynomial endomorphism of a commutative polynomial algebra in n variables, such that the Jacobian is invertible, is an automorphism. Since 2006, it was known, it was proved by Tsushimoto and independently by Belovka and Kantsevich, that Dixmier conjectures imply the Jacobian conjecture, and vice versa, Jacobian conjecture for two n variables imply the Dixmier conjecture. So it appears that these series of conjectures are stably equivalent. Anybody now knows that quite recently AI and Typology found a counterexample to all these conjectures for n greater than 2. The claim is that the original Dixmier conjecture for the first real algebra is true. Last slide, I try to explain what is the idea to get this proof. The original proof of Dixmier about the structure of the automorphism group of the first real algebra used the Newton polygons technique. The theorem of Dixmier says that the group of automorphism is generated by tame automorphisms of the following type. On the other hand, any endomorphism I of the first real algebra is given by a pair of operators Q and P satisfying the string equation. The known reductions to this conjecture says that if there is a counterexample to this conjecture, then there should be solution to the string equation of so-called subrectangular type. This means that the Newton polygons of the solution to the string equation has a subrectangular shape. Subrectangular shape means that the vertices, right upper vertices of Newton polygons of these operators must belong to the rectangle. So that all other points are inside these rectangles. In contrast, due to Dixmier theorem, any automorphism, which is also given by a pair of operators satisfying the string equation, are of triangular type. That means that Newton polygons of this pair of operators are triangles, which are proportional to each other. So to prove the Dixmier conjecture, it's sufficient to prove that there are no solutions to the string equation of subrectangular type. And this was a generic idea for this proof. The generic idea of this proof is as follows. We embed the first real algebra to the ring of ordinary differential operators. The ring of ordinary differential operators is embedded to a larger ring P1 hat C. And then I use generalized theory of normal forms, the theory of commuting operators to study solutions to the string equation. Considering a counterexample of subrectangular form, I multiply and make a family of counterexamples and apply this one-to-one correspondence to get a contradiction. So this is a very short idea. I have no time to explain more details now. So sorry for delay. And at this point, I'd like to thank everybody. If you have questions, please.
Thank you very much. Let's thank Professor Zheglov for a very clear and impressive talk. Thank you so much. Are there questions or comments? Please unmute yourselves or put the question into the chat. Well, maybe I can start with just a question on terminology. Why is the Weyl algebra equation called string equation? This
is terminology introduced by physicists. from string theory. Douglas, I think, was the first who introduced this equation, this terminology. And this equation was studied by many physicists and mathematicians, by Douglas, by Albert Schwartz, Novikov and Grinevich tried to study asymptotic behavior of solutions to the string equation. And as I said, Albert Schwartz obtained a similar one-to-one correspondence for operators of coprime orders. So anybody who is interested, you can look at his papers from the 90s and then from 2015 about quantum curves. So from that point of view, the study of solutions to the string equation is interesting from the point of view of string theory, because they are related to solutions to the Van der Waals equation.
I see. And the terminology quantum curve, it's also motivated by physics, or is there?
Yes. But now there are many, there are several definitions of this notion, quantum curve. For example, Albert Schwartz used this definition, namely he said that a quantum curve is just a solution to the string equation. That is a pair of differential operators satisfying this relation, commutator of P and Q equal to 1. But later, other people used other definitions. There are several versions of this notion, quantum curve. And it's an interesting question how they are related. There are really many papers about quantum curves from the people from string theory. You can check just by typing in Google quantum curves, and you will see there are really many papers about solutions of these quantum curves, maybe mathematical physicists from the community. But however, I asked Albert Schwartz and other people from this community, is it known any classification of such solutions? As far as I know, no, yes. My dream was to establish some classification of solutions to the string equation. For example, in terms of commutation operators. If you know the classification of commutation operators, I thought that this construction could give a classification of solution to the string equation. But however, as I said, just recently, this student found a series of examples which don't come from the commuting differential operators. So this question appears to be very interesting and old. I hope that maybe it will be interesting, especially string theory and corresponding topics.
Thank you. Let's see whether there are other questions or comments. I would have one more question at the beginning. You mentioned your joint paper with Igor Burban, which had, in particular, Cohen-Macaulay modules were involved over the algebra of planar quasi-invariants.
Yes.
Can you say a word about the link to Cohen-Macaulay modules?
Yes. In fact, this is an interesting topic. I had no time to explain this, that this theory of normal forms, show status theory, was applied to study quantum material systems in higher dimensions. And this is a topic for another talk, in fact. We tried to study known so-called quantum Colagero model systems from the point of view of this extended show status theory. Just roughly, let me show you another slide from another talk. to explain what is going on. Just yeah, I will share that slide. So, roughly speaking, we consider, say, commutative subrings of quantum systems in the sense of Braverman and Gates-Gopis work. If you say considers commutative subrings of two variables in the same sense, there is a one-to-one correspondence that establishes an correspondence between equivalence classes of such commutative subrings and certain algebraic geometric spectral data. But here, the spectral data is much more complicated. Now, spectral surface is a projective algebraic surface. Additional data is an integral ample Cartesian Q-Cartier divisor. And F is a covariant torsion-free sheaf of rank R, which is Cohen-Macaulay along curve. And in fact, it can be assumed to be Cohen-Macaulay globally. So in this classification picture, it's we need to know the modular space of Cohen-Macaulay torsion-free sheaves with fixed Hilbert polynomial. And in our work with Igor Bourbon, we tried to apply the Bourbon-Drost description of Cohen-Macaulay models on singular affine Cohen-Macaulay surfaces to explicitly describe this modular space, and then to calculate this spectral data for known examples of deformed quantum Zheglov systems invented by Zheglov, Charles, Stirkas, and Fakin and other mathematicians. And we were lucky we were able to explicitly calculate this modular space in terms of this category of triples by Bourbon and Drost. Then transform it to the language of Schur pairs, generalized Schur pairs from my work. And at last, we were able to find deformations of these examples of Algebra model systems. And another slide. The explicit example from that work looks as follows. So if you consider the centralizer of a Algebra-Moser operator in two variables, for example, this rational coefficient, then it was known from the paper by Chalov, Weyl, and Stirkas that this centralizer of this operator, of this isomorphic to a ring of so-called quasi-invariants, there is an explicit eigenfunction which was invented by Yuri Berest, and we calculating this modular space of sheaves, we could deform this eigenfunction and deform the operators themselves. So deformed Baker-Heiser function looks as follows. We take the best function and add some term of very explicit shape. And at the end, we get the deformations of commuting operators. Now these deformations determine some flow on this modular space of Cohen-Macaulay sheaves. But they appear to be not differential operators, but certain differential operators. And now this example was just the first example of an operator from this big ring D2 hat theme. They have a very explicit shape, again, where the operator S is given by this formula. It is almost differential, but it includes Dirac delta function, delta 2 and delta 1. So that was the first example, deformed example of this classification theorem. That is. And I expect that in the future, I could develop this theory of normal forms to produce more examples. So I am sure that we can study not only known examples, but construct new, as in this form. I hope that it's an interesting topic.
Yeah.
For
Yeah.
the
I think so. Thank you very much. Any more
Thank you for
questions or comments from the audience? Well, if that's not the case, let's thank Professor Zheglov once more. Thank you very much for a very interesting talk and discussion.
Thank you very much for your questions. And thank you for attention.
Well,
so then bye.
Bye.
Have a nice evening.
Thank you. Same to you.